Hello there and welcome back. In this video we're going to finish off our discussion of basic hypothesis testing for parameters of populations by focusing on how to construct confidence intervals for the linear regression parameters, the slope, and the vertical intercept. Keep in mind we are not going to be going through the theoretical derivations of these particular formulas, just discussing what they are and doing an example that goes through how to use them. So, firstly, we're going to be looking at a bivariate normal population. So keep in mind this is going to be a bivariate normally distributed population. That is, it's going to consist of two variables, x and y, coupled in a pair, where x and y are both continuous normal random variables. We're going to be calculating a sample or constructing a sample from this particular population, and then we're going to be calculating the line of best fit for that particular line. So for this particular population, let's assume that the line of best fit for the population is given by y is equal to beta 1x plus beta 0. So beta 1 is going to be the slope of the parameter line of best fit, and beta 0 is going to be the vertical intercept of the population line of best fit. So our first question is, of course, what is a point estimate for each of the parameters for this line of best fit? That's of course going to be equal to y hat is equal to mx plus b. So beta 1 is going to be approximated by m, beta 0 is going to be approximated by b. So m is going to be a point estimate for beta 1, b is going to be a point estimate for beta 0, and then those are hopefully going to be the middle of the confidence intervals for beta 0 and beta 1 with some standard of error. So, a couple things that we definitely should know before we proceed. First off, are they unbiased estimators? So one can show that the expected value of m actually is going to be equal to beta 1. So that gives us an unbiased estimator formula for the slope. Secondly, the next thing that we would find would be the variance of this random variable m. One can find that's actually equal to the sum of the squared residuals for our data set S divided by m minus 2 times the sum of squared differences for the x values of S. So before moving on, let us just briefly review what these things are. So the sum of scored residuals is going to be the sum of the residuals squared. So what is a residual? So remember, when we have a line of best fit, and let's assume there's some data points that it's approximating, the residual is just the vertical distance between the line of best fit and the y value, or the true value of the range. So of course, if this correlation coefficient is close to 1, that means the sum of squared residuals should be close to 0. So that's going to be, of course, equal to the sum from k is equal to 1 to m of yk minus y hat, k the quantity squared. We square it so we don't have opposite residuals canceling each other out. So then we're just going to have n minus 2, and the sum of squared differences for our x values is just going to be equal to the sum from k is equal to 1 to m of xk minus x bar the quantity squared. So that's all of those things. So that is the variance formula for the m, or the slope of the linear regression line. Now keep in mind we usually don't like calculating the sum of squared differences for x. So what we can do is we can actually multiply top and bottom of this equation by m minus 1, and then we can just treat this expression to be equal to the variance of x. And that gives us a nicer representation for the variance of m. So the variance of m can be rewritten as the sum of squared residuals for s divided by m minus 1 times m minus 2 times the variance of x. If you have the variance, you should be able to find the standard error associated to using m as an approximation for beta 1. So the standard error for m is going to be equal to, so once we take the square root of this, we're going to take the square root of the variance on the bottom, so that's going to be equal to the standard deviation of the x values, times the sum of squared residuals for s divided by m minus 1 times m minus 2, and that gives us a formula for the standard error of the estimate for m. Now, in case you are curious if there is a nice way to calculate the sum of squared residuals for a dataset, the answer is yes. It's a fun little exercise to prove that the sum of squared residuals for a bivariate dataset S is actually equal to the variance of y times m minus 1 times 1 minus the correlation coefficient squared, or the coefficient of determination. So this can actually be used very easily in order to construct these sum of squared residuals for S, so that you don't have to do that calculation manually. So once we have our standard of error, we just need some distribution that we're going to be using. So we're going to be using a t-distribution with degrees of freedom n minus 2. If that gives us a t-distribution for some random variable that I'm not going to mention here, that means we're going to be using t-critical values to construct confidence intervals. So the confidence interval for beta 1 under some level of confidence c is going to be equal to m minus our margin of error and m plus a margin of error. And this is going to allow us to test hypotheses about beta 1 is equal to some value, let's call it beta 1 sub 0. And of course this is going to be used for the two-sided alternative beta 1 does not equal to the claim value of beta 1. And that gives us the basics for hypothesis testing on the slope of the linear regression line. So what about the intercept? So one can show also that the expected value of the vertical intercept actually equals to beta 0. So that means B is an unbiased estimator for beta 0, which is great. And then you would, of course, go ahead and calculate the variance of this random variable B. So one can show that that's going to be equal to the sum of squared residuals for your data set S divided by m minus 2 multiplied by the quantity, 1 divided by the sample size of your bivariate data set, plus the arithmetic mean of your independent variables squared divided by the variance of x times m minus 1. So the derivation of that is definitely an algebraic journey. So if you can calculate the variance, that means the standard error for the vertical intercept is just going to be equal to the square root of that term. So the square root of the sum of squared residuals for s divided by m minus 2 times the square root of 1 over n plus x bar the quantity squared divided by the variance of x times m minus 1. And keep in mind that square root does not cancel those squares on that second fraction. So that gives us that formula there. So once we have our standard of error, we just need a distribution to calculate critical values. And again, we're going to be using a t-distribution with degrees of freedom is equal to n minus 2. Same exact one for before. So if we're doing confidence intervals for both m or beta 1 and beta 0, we can use the same t-critical value for both if we so choose to, but it's not necessary that the same exact alpha value is chosen for both. So once we have our distribution of confidence, that means the confidence interval for the vertical intercept under some level of confidence is just going to be equal to b minus epsilon, b plus epsilon, and that gives us the confidence interval for testing hypotheses of the form beta 0 is equal to some claimed value of beta 0, and beta 0, two-sided alternative, not equal to the claimed value of beta 0. And that gives us the fundamentals on doing hypothesis tests for the linear regression parameters. Now let us briefly talk about the interpretations of how you would actually use this in practice. For the interpretation of the confidence intervals for the slope and the vertical intercept for your linear regression line, I'm going to be approaching this from the geometric perspective since it's a little bit more easier to understand. We're actually going to be starting with the vertical intercept because that's actually more easier to graph and picture in your mind. So let's consider the confidence interval for the vertical intercept. So that's what B is approximating in this particular picture. So remember, the vertical intercept represents the point where it crosses the vertical axis. So let's assume that this is our bivariate data set, right? So if that's our bivariate data set, then of course there's going to be equal to some line of best fit. So this is going to be y hat is equal to mx plus b, where b is this number here, all right? So the confidence interval for this is going to be given on the vertical axis. So this is going to be equal to b minus epsilon and b plus epsilon. So if we keep our slope fixed, then the confidence interval for the vertical intercept gives us these two blue lines. So this line is going to be y hat is equal to mx plus b minus epsilon, and y hat is equal to mx plus b plus epsilon. So that gives us some values for which our data values can sort of fluctuate around this line of best fit. So small deviations around this line of best fit will be accepted as long as they don't fluctuate too far off. So one could actually use the vertical intercept confidence interval for detecting outliers in the bivariate world. Now, what about the slope confidence intervals? What would they look like? So confidence interval for beta 1. So what would they look like? So let's assume that we keep our, let's call it our vertical intercept fixed in this case. So let's assume this is our line of best fit. Y hat is equal to mx plus b. And let's change this m. So we're going to make our m a little bit bigger, and we're going to make our m a little bit smaller, and we're going to keep b the same, right? So if we keep b the same, that means our next line is going to be somewhere out here, hopefully not too far. So that's going to be y hat is equal to m plus epsilon x plus b. Then we're going to have another line down here. This is going to be equal to y hat is equal to m minus epsilon x plus b. Now, what is so special about this particular confidence interval? So this allows your data to expand through time. Now, this is extremely useful because error usually accumulates. Error usually accumulates through time. So this confidence interval on the slope of the line of best fit sort of accounts for that particular scenario. So those are the individual confidence intervals in isolation. Now, what about the combination of the two? So combination of confidence intervals. And let's take the extremes of both of those intervals. So let's draw our bivariate data set. So let's assume that this is our bivariate data set. Let's throw a couple outliers there. Why not? Let's assume that this is our line of best fit. So y hat is equal to mx plus b. Let's call this b plus epsilon, b minus epsilon. So our dotted line would be there. And our dotted line would be there for our y hat is equal to mx plus b plus or minus epsilon. So if I were to draw another line out here, so that's a slope slightly, I shouldn't be using the same color, right? So let's do a line slightly bigger than that, and let's do a line slightly less than that. So this allows fluctuations beyond and close to the starting values of our data set. So it allows errors to grow, and it allows minimal errors or perturbations from the line in the original starting point of our data set. So what is this first line? So this first line is going to be equal to y hat is equal to m plus epsilon m x plus b plus epsilon b. And this lower line is going to be equal to y hat is equal to m minus epsilon m x plus b minus epsilon b. Because these epsilons are independent from each other between the epsilon or the b and the m world. Why do I keep writing plus? Minus epsilon b. So those are the two confidence intervals for the extremes of this distribution. So let's just outline briefly some of the things that we notice here. So confidence interval for beta 0 allows for small fluctuations around the line. Confidence interval for beta 1 allows for small changes in the rate of change for your data set. So that allows for some small growth or some small decay in terms of the derivative of the line of best fit. And in general, both CIs allow for small changes and small accumulation of changes. So those are the main observations that we get for the confidence intervals for the linear regression parameters. Now let us look at a numerical example on how we could calculate both of these. So suppose that we are interested in studying the association between sleep quality and room temperature, and we consider a series of individuals and look at their average sleep quality in a controlled particular room temperature in degrees Celsius, shown in this table. So if these are the results that we get, what can we just see inferentially? So clearly, as room temperature increases, the values of sleep quality definitely decreases. Now, is this generally the world that we live in? Technically not, because if we look at the distributions for sleep, usually there should be a point where you're the most comfortable. Let's assume that this corresponds to the most comfortable position. Now, if we're assuming that sleep quality is normally distributed with respect to room temperature, that means the distribution is going to be associated to this. Therefore, if it's too hot or it's too cold, then the distribution should be something like this. So this is going to be temperature, and this would be sleep quality. Now, if this is the particular correlation that we're focusing on, technically we're only looking at this particular realm. So we're making the room a little bit hotter in the control variable sense. So if this is the world that we're living in and we're going to be using lines of best fits, we should be only focusing on one region of the monotonic behavior of this particular random variable. Because if you use both sides of this normal distribution, in particular the left and the right, the distribution for the line of best fit probably would look something like that, and you won't get any information that is useful from that line of best fit. So keep in mind, as long as your data is one-to-one, or if it's not one-to-one, partition it into several one-to-one sets, and then approximate that with a line and that with a line, and everything will be well. As long as you're assuming that it does continue outside of that region, so it really depends what you plan to do with this information. So let's assume that we're just focusing on the right-hand distribution because that's definitely the region that we are looking at. So the first thing that we need to do is calculate a couple statistics from this data set. So if you sort of try this on your own in Excel, you can find that the average value for a room temperature is going to be equal to 18.5 degrees Celsius, and the average observed sleep value is going to be equal to a 34.93 sleep score. The standard deviation of x is going to be equal to 1.87, and the standard deviation of y is going to be approximately equal to 2.72. So those are the individual statistics for each individual variable, and then you can calculate the covariance of this data set to be equal to approximately negative 4.52, and one can then calculate the correlation coefficient to be approximately equal to negative 0.8882. You could do confidence intervals for the correlation coefficient to determine if there is a significant evidence to support the claim that there's a linear association between these two. You can do your claim to be equal to, say, negative 0.95 or negative 0.98, and then see if that particular claim is inside the confidence interval that is mirrored or centered or sort of centered around R. So once you have these statistics, you should be able to find that the slope of the line of best fit is going to be equal to approximately negative 1.29. Remember that the slope is just going to be equal to the covariance divided by the variance of x, and you should also be able to find the vertical intercept b to be equal to 58.82. Keep in mind that's calculated by doing the average of y minus m times the average of x. So these are our point estimates for our linear regression parameters. Now let us state a couple of hypothesis tests that we want to choose. So firstly, let's assume that somebody claims that the slope of the line of best fit for the population is equal to 1.5. And let's do an alternative that beta 1 is not equal to 1.5. And let's assume we want to be testing this with an alpha value for, let's call it alpha A, to be equal to 11.2%. So one can ask, well, is negative 1.29 close to negative 1.5, or is it significantly far from it? If it is significantly far, we will reject this claim. Our second hypothesis test that we're going to be looking at is the null hypothesis claim that beta 0 is equal to 80. So again, we need to ask, is 58 significantly close to 80 or not? Let's do a two-sided alternative for that, where beta 0 is not equal to 80. So anything significantly higher or significantly less than this number will be perfectly fine. Let's do a different alpha value for this, because they need not be the same, of 14.7%. because some of these parameters we would like more variability in, and some we would like the variability to be very, very small. That's why these alpha values need not be equal to each other. So the very first thing that we need to calculate is the sum of squared residuals for this data set. So the sum of squared residuals for this data set S, that is the next thing that we definitely need to calculate. And remember, the sum of squared residuals is approximately or exactly equal to each other, equal to the variance of y times m minus 1 times 1 minus r squared. At this stage, you have all of these elements, so you should be able to calculate this with no issue. Or you can do it manually in Excel, and that's perfectly fine as well. That's going to come out to approximately 7.81. The next thing that we need to calculate is the sum of squared differences for our x values. So that's going to be equal to the variance of x times m minus 1. So that's going to be equal to 17.5. Once we have these elements, then we are ready to go to calculate our critical values. So remember, since our data set was equal to 6, that means our degrees of freedom for both our critical values for both beta 0 and beta 1 is going to be equal to n minus 2, which in this case equal to 4. Keep in mind, alpha A was equal to 11.2%, so you should be able to find the level of confidence for the first parameter, and alpha B was set to be equal to 14.7%. So one can also find that the t critical value for hypothesis test A is going to be equal to approximately, let's actually label them with the parameters that they're estimating for. That's going to be beta 1. It's going to be approximately equal to 2.0317, and the t critical value for beta 0 is going to be approximately equal to 1.7955. Now that we have our t critical values, we just need our standard of error for each of these parameters. So the standard error associated using m as an approximation for beta 1, remember, is going to be equal to 1 over the standard deviation of x times the square root of the sum of squared residuals for our data set, divided by m minus 1 times m minus 2, and you can find that that's going to be approximately equal to 0.334. The standard error associated using b as an approximation for beta 0, remember, is going to be equal to the square root of the sum of squared residuals for s divided by n minus 2 times the square root of the reciprocal of the sample size plus the average of our independent variable squared, variance of x, n minus 1, and that's going to come out to 6.205. Usually the slope margin of error is always going to be significantly different than the standard error of what you're using, but that's necessarily not the case, but usually the case for basic studies. Now that we have our t-critical values and our standard errors for each of our point estimates, we simply multiply these two things together to get our margin of errors for each of our confidence intervals. So once you go ahead and do that, the confidence interval for beta 1 under a level of confidence of 88.8% will come out to negative 1.97 to negative 0.61, and the confidence interval for beta 0 under a level of confidence of 85.3% will come out to 47.7 to 70.0. So let's recall what our null hypotheses that we were testing against. So the null hypothesis for beta 1 was beta 1 was equal to negative 1.5, and the null hypothesis for beta 0 was that it is equal to 80. So, since negative 1.5 is in between these two numbers, then we're going to be failing to reject this null hypothesis claim that the beta 1, or the slope of the line of best fit for the population, is exactly equal to negative 1.5, and one could go through interpretations and applications of that conclusion. And since 80 does not fall in between the beta 0 boundaries, that means we're going to be rejecting the claim that the vertical intercept for the population line of best fit is actually equal to 80. We actually have evidence to believe that it's something significantly less than that. So those are the foundations associated to hypothesis testing for the linear regression parameters. There's definitely a lot of applications that one could get from this, for example, stock market and investment analysis, but we're not going to be getting into them at this time. Anyway, I hope you enjoyed this discussion on hypothesis testing for linear regression parameters, and I will see you in the next discussions of statistics. Take care.